Hi everyone, Alicia McGill here with Math Labs, and today
because you know I'm all about that bass, no trouble.
I'm all about that base and the exponent to the power. Okay, I can't sing, but I know math. I'm a mathematician and so are you, and that's what we're going to do today. We are going to do math. We are in Lab 1.2 of the Math Labs book, Grade 8 Expressions and Equations unit. This corresponds with Common Core State Standard 8.EE.A1, and we're focusing on the mathematical practices 1, 2, 7, and 3. I put that out of order because I really looked at 1, 2, and 7, and then I remembered, wait, Part C, they have to critique the reasoning of others and justify their reasoning for the simplified answer. And so that's huge, right? And there are going to be a lot of claims being made about properties of exponents that we're going to explore. But number 7, that's repeated reasoning. Kids are going to be involved in looking at their answers in the simplified form in a table and then look for a shortcut. And that's all mathematical practice number 7. That is so good. That's what Math Labs is all about. So we have a fun one today. Our vocabulary words, our base. Here's the base here, x to the exponent power 3. But you already know that, so I'm not going to go over that. Product of powers is new, and quotient of powers. And you might see those differently. They might be expressed like a power multiplied by a power, not necessarily product, but we all know that that means a power times a power. All right, and so let's get right in. This is Lab 1.2. So open up your lab book to 1.2 and read the objective in your head as I read it aloud. Here we go. I can use and apply the properties of exponents. Okay, so we're going to use the properties of exponents and we're going to apply them, all right, to situations and scenarios. But first we need to know how to discover these shortcuts that are going to help us to understand and be able to use the properties of exponents. Okay, so let's get right in. The first example, really before I get to that, I want to just recall with you and tap in your prior knowledge, x to the third. Everyone just recall that x to the third, I wrote it backwards for you this time, no one ever writes the exponent first here, is really expanded out as x times x times x, right? And we know 5 squared is not 10. We know that that's a common error, but it's 5 times 5, which equals 25. So numerically we can come up with answers simplified, but we're going to write our answers in exponential form. And don't worry about that word right now, but it just means a base to an exponent as opposed to expanded form. We're going to go back and forth though so that we can discover our shortcut. Alright, so now that we recall what a base and an exponent, what they are and what they mean, let's look at this first example. I'm going to start with numerically. 5 to the third here times 5 to the fourth. Okay, so we're going to first start by expanding. What does 5 to the third mean? Alright, and I'm going to just here do this in, the base is blue because I'm all about that base. And this means 5 times 5 times 5, right? That's 5 to the third. And 5 to the fourth means 5 times 5 times 5 times 5. And all together, that's 5 to the power of 1, 2, 3, 4, 5, 6, 7. Okay? So what you're going to do in your table is you're going to have the problem written, 5 to the third times 5 to the fourth, and you're going to have your simplified answer, which is, we're going to call it exponential form because we're using an exponent, and it's simplified here. And this is how we arrived at our exponential form from the expanded form here when we expand that out. Don't worry about those words, just understand that, you know, just like an accordion, this is expanded. You know, I wish they call this contracted form, right? Expand and contract. But it's not. It's exponential form because it uses an exponent. All right, let's look at the algebraic example. See if you can apply this using variables. So let's just use m to the 6 times m squared. You know what? Let's challenge here, times another m. Now, what power is this m? Many of you recall that that's to the first power. And so when we expand this out, essentially, we have m to the 6, right? That's a lot of m's. Yummy. M. I like M&M's. There's 6 of them. 1, 2, 3, 4, 5, 6 times m squared. So that's 2 powers. Remember, we're not adding, we're multiplying. times n to the first, or that's just times n. All together here, when we count n to what power, we see it's m to the 1, 2, 3, 4, 5, 6, 7, 8, 9th power. So our exponential form is m to the 9th power, and this is what it looks like expanded. All right, so again, you will work on expanding and then writing the exponential form, and in the table, you're only going to write the problem and the answer, and that's going to help you generate a shortcut, which is what good mathematicians do, right? And that's who you are. So let's look at, that's all part A, that's product of powers, because we were multiplying a power times a power. Now let's look at quotient of powers. So let's start with a numerical example. So I'm just going to here do, I don't know, 4 to the 8th divided by 4 squared, or 4 to the 2nd. 4 to the 8th is 4 times 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 4. All over. So what I have to do here is I have to expand the numerator and the denominator, because we're looking at quotient of powers. And just recall that anything over itself is 1. That's something to just remember, like 12 divided by 12 is 1, right? Anything divided by itself is 1. So, because 12 wasn't a 12 one time. So when we expand this out, we are going to be canceling out 1s in just a moment. 4 squared is 4 times 4, so I'm just going to write that here. Now, to simplify this, we don't count, because that's not what we have here. We have to simplify, and like I just stated, 4 divided by 4 is 1. So we're going to cancel these out, and we're going to make this a 1, and this a 1. So our numerator is 1 times 1, which is 1, times 4 times 4 times 4 times 4 times 4 times 4, which equals 4 to the 1, 2, 3, 4, 5, 6th power. Okay, over essentially 1, but we don't need to write over 1. We know that 4 divided by 4 is 1 divided by 1, so we could, but when we think about numbers like the number 10, we know that that's the same as 10 over 1, but we need not write it here. So this will be our final exponential form, 4 to the 6th power. So again, in your table for part B now, you're going to write the problem and then the simplified answer, so that you can generate a shortcut and look for that repeated reasoning, and so that you can say, I think I know how to simplify this without actually drawing the expanded form. Now, let me just say that this expanded form is important, and even if you feel like you've already generated a pattern and you're like, I got it, I know how to simplify it, I still want you to write them out. There's not a lot to do, and all of the exponents are less than 12. But it's important to do that, because when we look at negative exponents, which we will, it's this idea of expanding here and having this 4 to the 6 remain in the numerator is important to understand that concept. So don't be frustrated because you have to expand it out. It's only one lab of doing that. It's only one part B, and the exponents are easy to do. So now that I've convinced you that this is good for you, let's look at the next example. You're going to do this one on your whiteboard, okay? So if you don't have a handy-dandy whiteboard, you can just, use scrap paper. Oh, hey, let's just throw everything on the ground here. All right, so we're going to look at quotient of powers, and let's look at algebraically. Let's see, how about W to the 9th power divided by W to the 3rd, or W cubed. So we have W to the 9th power. So if we were to expand that, that would be W times 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 W. I know. And then over W times W times W. Okay, I know that took me like all of 10 seconds of my life, but it's important it's all for the cause. It's all for mathematics. This is great. All right, so we're going to